Thank you. This is actually my second time at Mila. The last time I was here was the old location, so it's nice to see it grow and yeah, succeed as much as it has. So today I'll tell you about this effort that we've had. It started out as basically a kind of a reproduction of AlphaFold2, the system that was developed by DeepMind for protein structure prediction. And it's now sort of going into this consortium, an industry sort of academic consortium that's trying to tackle problems more broadly in the molecular sort of modeling space. But before I do that, just make sure everybody's on kind of the same page. What I'll first do is spend maybe the first 10 minutes telling you about essentially what the AlphaFold development really kind of means for the field, what it did and what sort of remains to be done. And then I'll kind of pivot into talking about OpenFold and some of the work that we've done, in terms of again, reproducing AlphaFold2, but also sort of learning and deriving some new insights from the kind of the training effort that we turned into rebuilding it from scratch. So just to begin with, in case you're not familiar with AlphaFold, the system was developed a couple of years ago, and the focus was on protein structure prediction. So given a sequence, can you predict the three-dimensional structure of that protein, given a protein sequence? And this is a problem that's sort of preoccupied biochemists for the better half of a century. It sort of was kind of seen as kind of sort of grand challenge in molecular biology. But it's worth sort of noting that it's really one of a kind of constellation of problems having to do with molecular modeling, right? Particularly sort of protein-focused molecular modeling, including things like protein-protein interactions, predicting the binding of a small molecule into a protein pocket, nucleic acid interactions with proteins, and so on. So there's a whole concept of constellation of problems that we're interested in broadly as a community. So coming back to AlphaFold2, just kind of by way of background, because of the centrality of this problem, and because for many years there were sort of claims of a solution that didn't really sort of pan out, about 25 years ago, a community was organized called CASP, with the intent of essentially sort of rigorizing, if you may, the process and of the assessment of protein structure prediction. Right? And in particular, it was set up so that the quality of the methods that were being developed could be assessed in a completely blind fashion. So there's no kind of danger of leakage or what have you. And so typically the way this is done is every 2 years, new structures that have been determined experimentally, but they haven't yet been released into the public domain. Those structures are typically sort of given to this kind of private organization before they're released. And then the sequences of those structures are presented to different prediction groups to predict those structures kind of completely blindly, and then that allows a sort of an assessment to occur. So what I'm showing on the left side here is the performance of different methods at CASP, the best methods at CASP, during the 2010s, right? And I would say for much of the 2000s and the middle of the 2010s, there was really very little progress. So the y-axis here is RMSD, which means square deviation between the prediction and the ground truth structure. And experimental methods are sort of within an angstrom based on this sort of metric. And what you see is that those methods were sort of north of 10 angstroms at the prediction quality. So quite poor. And this sort of character, is kind of up to say 2016 in this case. And this characterized the field for, like I said, for really more than a decade. It was a sort of widespread stagnation. People were kind of stuck. That began to change with the first AlphaFold, where as you can see on the slide, there's a precipitous drop in the RMSD, and even though it sort of was not yet to the level where it was biologically useful, the predictions were still pretty poor, but methodologically, it meant a lot to finally see the substantial progress that hadn't happened, for decades. I should say that in this particular instance, in the first AlphaFold in 2018, I would argue that much of the innovation was really more engineering driven. So there were not any kind of new sort of conceptual breakthroughs. It was sort of just DeepMind kind of really pulling the resources and being able to do something that few academic groups could do well. But this really changed, as you can see, with AlphaFold2, right, in 2020, where now, and I think maybe more importantly, the accuracy was sufficiently high. So this became interesting to biologists, right? Now you could derive insights from these predicted structures that you couldn't do before. And that was, I think, a sort of really a sea change. I would argue almost a sea change for computational biology at large, because it's, for a long time, I would characterize the field as being a bit insular, and in the sense that it didn't interact very much with the broader biology community because of the fact that the methods were sort of not yet good enough to be of broad utility. Right? So they were sort of interesting for the method developers, but they didn't move the needle on the science itself, right? On the biological science. But this really changed that too. And then methodologically, I would argue that the sort of innovations that had to be developed to do AlphaFold2 were really sort of conceptual in nature, right? There was legitimate kind of new advances in terms of how the system was architected that allowed it to do as well as it did. And this was not necessarily maybe true of the first AlphaFold. And I think that made it even more exciting, as I'll talk about in a moment. I think it's the kind of the innovations that arose in AlphaFold2 now have since percolated throughout the field in many other kind of molecular domains. Right? And that's I think been kind of the second payoff. And just by way of reference, the blue and green are superpositions of structures predicted by AlphaFold and experimental structures. And as you can see, they're usually in sort of high superposition. So before I kind of start telling you about what sort of what OpenFold and what we're working on next, let me mention a bit in terms of kind of what AlphaFold can and can't do, right? So at that CASP competition, the median accuracy that it achieves is about 2 angstroms on essentially sort of single proteins that are by themselves, which is incredible for what it was. But it does begin to struggle a bit with, say, multi-domain proteins. So those are often very large proteins where you have these sort of modular components that are strung together to kind of form a larger complex, as you can see here. Where now you begin to see some sort of deviation from the experimental structure. Some of that may simply be driven by flexibility in those domains, but nonetheless, it's not entirely sort of clear yet how well AlphaFold does in that context. Where it begins to seriously struggle is when you're considering mutations, right? So for example, if you have a variant of the spike protein in SARS-CoV-2, how that variant changes the structure is not something that AlphaFold can really do very well right now. And that's broadly true for any kind of prediction, in part because the way it makes its predictions is based on sort of effectively averaging a whole bunch of different sequences, hundreds to thousands of different sequences that are related to the protein of interest. And by that averaging, it's sort of able to kind of extract evolutionary information that sort of corresponds to spatial relationships in the protein structure. But if you have a single protein and you really care about how that protein is distinct from another protein that's similar to it, that's not something that AlphaFold can do, at least as of now. Now, going beyond that, things that it can't handle at all are ligands, cofactors, modified amino acids. So when you really kind of move into the chemistry domain, if you may, and it's no longer about proteins and amino acids, but different kinds of chemical moieties that are not simply sort of represented in the AlphaFold2 system. It's not a fault of the system. It's just simply not capable of representing it as it's currently architected. One sort of last point on AlphaFold before I move on. One nice thing it did, and I think is responsible in part for its sort of widespread adoption, is that it makes calibrated predictions. So it doesn't simply make a prediction about the structure, it also makes a prediction of the likely quality of that structure. And that's what you're sort of seeing here, where on the y-axis is the actual quality of a given structure, 0 is bad, 1 is good, and on the x-axis is the predicted quality of that structure based on AlphaFold2's assessment. And you see that most predictions on the top right, so they're generally quite good, but there's also a reasonable correlation between the quality of the prediction and AlphaFold's sort of assessment of its own quality. And this is sort of, pictorially, it gets sort of mapped onto this sort of color spectrum onto the structure itself, where blue is high quality, red is sort of indeterminate quality. And that's very useful for biologists, right? Because you could immediately look at the structure and be able to sort of conclude where you could make reliable inferences, right? Or where you have to exercise more caution, right? And that, again, from a practical standpoint, made it just much more practically sort of useful. And I think is responsible for its success. I'll come back to this in a moment in terms of how the model begins to learn the self-calibration, which is interesting in its own right. Okay, so now let me sort of pivot to sort of our own effort with OpenFold. I should say, just to be clear, I had nothing to do with AlphaFold2. Of course, this is all DeepMind's work. When DeepMind released the system, I think they were quite good about being public and sort of open and accessible about it. But they did, and they released the code for the inference code, so you can make predictions very easily. But what they did leave out is the training code, right? So and it has a fairly complex training regimen. It's not really sort of a simple kind of off-the-shelf system as far as training is concerned. So there's a lot of sort of work that had to be done to kind of build that out, to be able to train a system from scratch. And we thought from the very beginning that it would be nice to be able to do this, right? For many reasons that I'll talk about in a moment, to essentially have a trainable version of AlphaFold2. So let me sort of motivate a little bit why we thought this was worthwhile. And we really had sort of 3 initial motivations. The first was, essentially being able to scale to fully retrain a model from scratch, right, for new applications. And I'll show a bit of this momentarily in terms of instances where this was clearly of utility. It was sort of worthwhile to be able to retrain a system from scratch, even without changing the architecture in any measurable way. The other is to kind of modularize the system, right? So the initial sort of release, it was in JAX, which is perfectly fine, of course, but PyTorch is sort of very widely used, and so we thought it would be nice to kind of implement it from scratch and modularize the system so that people can mix and match those components in various ways, and I'll talk about that in a minute as well. And then the last bit is we thought, first from a scientific perspective, right, it was quite important to have a kind of independent production, right? The paper described the method in detail, but we had no sort of independent verification that we could simply take the PDB, the protein data bank, train the system on that, and then get the same results, right? And from a reproducibility standpoint, that seemed like a worthwhile thing to do. The other thing, and this, so we almost kind of discovered it as we did this process, was that there was actually a lot to learn now from this process of actually training the system. And that we thought was quite valuable. And that's where I'll spend most of my time on today, but I'll walk through all of them sort of quickly. So one area that AlphaFold didn't do initially was predicting complexes. So if you have two proteins or multiple proteins, and you're interested in the arrangement of those proteins with one another, that was no sort of feature that was built into AlphaFold. And it was not something that AlphaFold was trained on either. So AlphaFold was simply given just individual protein structures. But very quickly after its release, a few enterprising people really figured out a way to essentially trick it to predict structures of complexes. And the idea was very simple: is that you take two different proteins, you essentially stitch them together with a flexible linker, which is actually what people often do in the lab experimentally. But here, this was all purely in silico. So you just simply take two protein sequences and concatenate them with some sort of repeating region. And then you feed that sort of single protein, but it's not, of course, single protein, to AlphaFold. And lo and behold, it actually produces the structure of the complex most of the time reasonably well. And just from a machine learning perspective, this is really interesting, right? Because this is a fairly dramatic distributional shifts with respect to the training data, because it's never seen multi-protein complexes. But it likely suggests that there's enough within kind of the protein folding process to teach the system about how protein complexes interact with each other. But anyway, so this was sort of a really nice kind of breakthrough, and essentially discovered over Twitter. It's sort of a funny, just kind of real-time discussions that led to this, and it led to several groups like the Baker Lab, for example, applying the system across the yeast sort of proteome and predicting all kind of the core eukaryotic machinery of the system. And there's been some applications to the human proteome as well, although maybe with a little bit less success, at least so far. So coming back to this question though, so what I'm showing you here are different systems, the performance of different systems on this task of protein complex prediction. The one in green, the one kind of in the middle, is a kind of a pre-AlphaFold2 system. This was what I would call the state of the art at that time. And here again, 0 is sort of bad, 1 is good. So you want this to be as close to 1 as possible. The other systems, excepting the top cyan, those were all this idea, the kind of the linker idea, right? Taking two proteins, concatenate them in some way, and then feeding it to AlphaFold2 with some additional tricks. But the key point here is that these systems were entirely based on the, not just the code, but the model weights that DeepMind released, right? This was just the vanilla AlphaFold2 applied in this new context. And they did quite well. I mean, to be clear, right, there was a qualitative leap over the kind of pre-AlphaFold2 system, right? So this was really exciting, because with very minimal effort, you got this, sort of state-of-the-art system. But the key takeaway here that I want to kind of emphasize is the top cyan, right? And that's AlphaFold2 multimer. So this was a system that it was almost identical to the initial AlphaFold2 that DeepMind had, and they simply retrained it now on protein complexes instead of individual monomers, right? And as you can see there's yet another sort of leap in accuracy versus kind of what it was the state of the art prior to it, right? So this, I mean, maybe this is sort of obvious to this crowd, right? But it obviously kind of pays to retrain on new data, right? Retrain, actually, retrain from scratch, both. Yeah, so it was a fresh retraining with monomers and multimers. Yeah, right. Then that's an important point. I don't want to oversell the point. There was some modification to the architecture. So it's not, the weights are not directly compatible with the previous one, but there were fairly minor modifications. Yeah. So it depends on how you count things, because proteins are evolutionarily related, and so there's redundancy in sequence space. So sometimes you could get perfectly identical proteins, even though they're two different experiments. I would venture probably on the order of maybe about 10,000, like reasonably non-redundant complexes. Sorry, what was the question? 10,000 complexes, yeah. As something on that order. But again, with redundancy, so there's a two-step procedure. The initial training set is probably more on the order of 50,000, but then they do self-distillation, where they predict these structures and they take the high confidence ones and retrained on it, and that bumps it to about 300,000. Yeah. All right. Right. So again, this was kind of I think an argument for being able to do this from scratch. The modular components one is again kind of a more natural argument for software engineers, right? So AlphaFold2 has a whole bunch of components, right? And some of these are geometrically sort of really interesting, right? So in particular, there's sort of notion of a triangular attention update, which is essentially a sort of an attention mechanism, a standard attention mechanism with a little bit of geometry in there, right? It's just a slight bias toward essentially respecting the Pythagorean theorem, essentially the triangular inequality, right? So just making sure that if you have three atoms that they form a triangle, and then there's the kind of mathematical constraints in terms of the distances that they could take on. These constraints are not hard, right? These are sort of soft constraints, but they're nevertheless there to kind of incentivize the system to behave in a certain way. Okay, so these components are broadly useful for any kind of geometric reasoning, right? So pretty quickly, we started seeing systems for RNA structure prediction, for inverse folding, where you take the structure, go to the sequence, for protein design, that started sort of incorporating these components into their architecture, right? And so again, this is sort of an indication that you want to be able to sort of take these general primitives and use them in new contexts. And this was my point earlier about AlphaFold2 sort of innovating on the architectural side. There were these new primitives that were sort of, I think, genuinely kind of interesting, and people wanted to use them in all sorts of places. All right, so now let me kind of get to the meat of the matter. So like I said, we sort of embarked on this effort to kind of completely rebuild the system from scratch. So this is not a sort of it's a new code base in PyTorch, like I said. And the kind of the first order bit is that it seems to produce AlphaFold2 perfectly. So that's really good news, right? So OpenFold is on the y-axis, AlphaFold2 is on the x-axis. Each dot is a protein. And you see that they're highly correlated. There are instances where one does better than the other, but those are generally, you could sort of assume there's just a stochasticity in the system. There are a lot of stochastic components throughout the pipeline, and so this is not surprising, but it's sort of an expectation that they're indistinguishable, statistically speaking. And this is what a sort of prediction looks like. So the white is the crystallographic structure, the blue is AlphaFold2, the pink is OpenFold in this case, and generally speaking, the agreements look like this. They're highly concordant. I will say a sort of couple of technical points is while we were implementing it, we actually managed to make a few things better. So it's faster. The implementation is about 3 times faster on smaller proteins, which matters if you're trying to apply this on a large scale, which often people do. We've incorporated sort of various kind of low memory attention mechanisms to make it sort of on sort of standard off-the-shelf GPUs. You could get it to infer on sort of larger protein complexes and things like that, which are sort of practically useful points. And one thing we did end up paying for is that enclosed complexity. So things that were sort of very tightly coded end up sort of being much bigger because of all these various optimizations. But we think for sort of production uses, this is a worthwhile trade-off. Now, some technical points into the precision and so on, but I'll skip these because I want to get to the more interesting pieces. So let me just one quick point into the convergence, right? So one question was, how much compute do you need to train the system, right? So we trained it for about a couple of months on 404100 GPUs, which is obviously a fair amount of investment for an academic lab, right? But not surprisingly, maybe the model does exhibit very fast convergence, right? And so in the first couple of days, you get to get about 90% of the final performance, right? And this is important, right? Because if you are interested in sort of training this model for new problems, you want to be able to kind of iterate quickly, and you don't want to wait, well, depending on how big your cluster is, but still you don't want to spend a few 100,000 GPU hours every time you want a new variant. That seems like it's too much. And there were some other aspects of the training. It's a multi-stage procedure, and we discovered, for example, that some of those multi-stage procedures, which are again very expensive from a training perspective, actually have fairly negligible impact into the final accuracy. Okay, so now as we started sort of doing this, we began to sort of unpack some of its behavior as it learns. Let me just say one quick point here. So in this curve, right, the first 5,000 steps is where kind of the most of the learning happens. Right? That's where that again a very quick spike, and that's what I'm going to focus on for essentially the remainder of my time. Just to what actually happens in that first 5,000 steps. So I mentioned the kind of self-calibration issue, right? So what I'm showing here is each dot is the model evaluated on this validation set, right? So this is an average over many proteins. And the color corresponds to where it is in the training process, right? So the blue is kind of the beginning of the training process, red is in that final kind of once it's slept up. And the y-axis here is again the actual accuracy of its predictions, and the x-axis is its predicted accuracy of its prediction. So what you see, which is sort of interesting, right, is that the model sort of starts out maybe a little bit overconfident, becomes underconfident in the middle, and then eventually sort of begins to kind of converge to this final state where it is sort of correctly calibrated. But nonetheless, throughout this process, the model, once it passes that initial phase of training, becomes reasonably well calibrated, right? So even in that kind of greenish yellow stage, where it's quite poor, generally speaking, in its prediction quality, it's still able to actually assess the fact that it is pretty poor in its prediction quality. And so self-calibration sort of emerges pretty early on. Even the quality sort of takes another several thousand steps before it becomes actually quite performant. We also analyze how it begins to learn structure, particularly in terms of secondary structure elements. So if you're familiar with proteins, there are certain kind of local bonding networks having to do with what I call alpha helices and beta sheets that describe, again, a more local geometry of the protein. And these have sort of fairly characteristic kind of patterns that we can detect computationally. So what seems to happen, so the alpha helices part are fairly local. They're very, they're 10 residues, 12 residues long, and they tend to be, in very kind of adjacent regions. Sheets, on the other hand, can be quite distributed, and they sort of come together, across wide long-range interactions across the protein to form these sort of motifs. So perhaps not surprisingly, helices are sort of learned first before sheets. This is the F1 score, so again, 100 is good, 0 is bad. But there's definitely kind of a discrete pause between when the first is learned and then the second piece is learned. And we see that across not just beta sheets and alpha helices, but other types of secondary structure elements that are a bit more, let's say, niche. So for example, polyproline helices, this is a much more uncommon type of secondary structure element. That's the one in the bottom gray. You see that takes a much longer time to learn. And it contradicts a little bit what I said earlier in the sense that that sort of 90%, performance in the first 2 days doesn't really apply to the polyproline case, where it takes, it does actually sort of take that full 100% of training time to finally get it to the performance that is sort of more, more competitive. But across the board, we see this sort of staggering in terms of how the secondary structure elements are learned. Generally speaking, correlated with the frequency of the elements in the data set. So not necessarily surprising in terms of what it learns when. It also seems to learn at sort of multiple spatial scales. So what we did is we took the structures and we kind of sharded them into small pieces, ranging in length from 10 amino acids all the way to the full length protein. And the color here indicates the size of those shards. And then again, we asked, how does the performance vary across time, right? So it starts out poorly predicting everything. It ends at reasonably predicting everything, right? So you see this kind of convergence of the tail ends. But in the middle, there's this sort of staggering where the shorter fragments are learned more quickly than the longer fragments, suggesting perhaps that sort of it begins to learn kind of more local aspects of structure before it learns global structure aspects, which is, again, not surprising, but it's sort of good to see that. And this is true even for the secondary structure elements themselves. So if you look at helices, for example, of varying length, you see this sort of this kind of separation in the beginning, where shorter ones are better predicted than longer ones, but that eventually all kind of flattens out into sort of equally well predicted independent of scale. So it sort of essentially becomes somewhat scale independent, but in the beginning it's not. And a similar phenomenon for beta sheets, depending on how many sheets you have. The final bit about sort of the geometry of learning, if you may, is that it seems to learn essentially kind of a spatial progression of the structures. So this is the model making predictions as it's being trained. And what it does is sort of first learns essentially kind of 1D lines, then what looks like sort of two-dimensional kind of curved sheets, and then finally sort of acquires three-dimensional volumes before it starts filling in the secondary structure elements that I referred to earlier, the alpha helices and the beta sheets. And this is not sort of cherry-picked. And every structure we looked at has a similar phenomena. So this is another structure, and again, you see sort of a similar kind of progression. This is likely driven by the loss function that's sort of trained on. But just I pointed out here because this is not sort of a foregone conclusion. Other protein structure prediction systems, including ones we've developed, don't necessarily behave in this way. They don't sort of have this kind of spatial progression in terms of learning, 1, 2D, 3D, and then finally the volume. Yeah. Yeah, so one sort of common theme that was sort of true, I would say, throughout this field prior to AlphaFold was the idea that you want the system to be sort of physical throughout the process. So for example, what that means essentially is that you would impose constraints on sterics. You don't want things to be collapsed. You always want to make sure that atoms are apart from one another, right, throughout the process. And this was taken very seriously, and essentially all the systems that we developed sort of respected that constraint. AlphaFold very much clearly breaks that, right? Because predicting these things that are 1D, 2D, and 3D, like I said, where certainly in the early phases of training, it's entirely non-physical, right? So at least one takeaway from this anyway, for us, was that this was a fairly key feature of the system. Because if you had actually imposed the steric constraints like all the other systems had before, you'd never have been able to see it take this sort of progression. I suspect there are other lessons to be learned from this, but this is sort of one example of actually, in a way, and it's a bit of a post hoc justification in this case, but of the value of not respecting these sort of otherwise physical ideas or physical concepts in this case. Okay, so let me skip a little bit since I only have 5 minutes. Which, yeah, okay. So I'll skip some of this stuff because I want to get to this part, which I think is very interesting as well. So Alpha was trained on the whole PDB, but it stands to reason that in many other data modalities, particularly when you think about small molecule, for example, where you have a lot less data and how much data you have may very well derive how well you do in these. I mean, that's an obvious statement in machine learning, how well you do in the system. So one question we wondered is, how well would AlphaFold2 have done if it were trained on much smaller data sets that maybe resembled what the PDB looked like 10 or 20 or even 50 years ago, okay? So the first thing we tried is, well, what about if we simply just reduce the data set, right? So just take the PDB and then randomly subsample it to a much smaller fraction than the full one, right? All the way down to the 0.76 there is less than 1,000 structures. So really, a very, very small data set. Not surprisingly, there is a reduction in performance. But what's remarkable here, right? Even that blue one, which is just over 0.6, that system is actually more performant than the first AlphaFold, the one that preceded it 2 years ago, which in itself was sort of considered a breakthrough, right? And so, there's often this kind of discussion, particularly in the kind of the BioML community, which is, how much does model innovation matter vis-a-vis data set size? Right? Do you just put all your effort into getting more data, or do you sort of bother with kind of being clever about the machine learning? And this, to me, is very clearly kind of an endorsement of the latter, right? Because what this is demonstrating is that AlphaFold2 is essentially 100 times more data efficient than AlphaFold1. That, given 100th of the data that AlphaFold1 had, AlphaFold2 can actually exceed its performance. And that's at least for again, the BioML community, that's an untrivial statement, right? That the architecture was able to kind of extract so much more information out of what it was given. So those are sort of, you could argue, random data reductions. And so maybe they will still essentially reflect the diversity of the data in the PDB, and that's not maybe representative of what you maybe see in practice, right? So what we also did was consider these structural kind of stratifications of the protein data bank, and these have been done, by others for decades now, where people sort of organize protein space into sort of different classes based on spatial relationships, based on spatial similarities. And these kind of range from what they call topologies, which are sort of low-level changes in structure, all the way up to class, which are sort of very large groupings. So class corresponds to like mainly alpha helical or mainly beta sheet proteins. So these are really big groups, essentially dividing the PDB into like three different categories. So very large splits. So what we did here was to now essentially hold out entire topologies, right? And then test on the held out ones. So now we're sort of structurally stratifying the PDB. Here you do see more of a hit. Not surprisingly, particularly with the blue, but again, certainly with the green, which is just seeing 10% of all topologies in the PDB, you're actually seeing a system that's more performant than AlphaFold2. And this remarkably holds for architectures, and in fact, all the way up to classes, right? So this to me was very, very surprising, right? Because here we're essentially only training on mainly alpha proteins, right? And assessing how well we do on beta-dominated proteins. And then we do the converse. And again, clearly a hit, right? This is not performing as well as AlphaFold2, but remarkably, this is doing better than AlphaFold1. And so again, going from a distributional shift, I mean, this is seeing a very, very kind of non-random region of protein space, and yet it's able to actually sort of generalize to that unseen region. And this is just kind of pictorially what you can see, right? So the top one is the alpha chained model tested on, the top is an alpha helical protein, the orange is the ground truth structure, the pink is the alpha trained model, and the green is the beta trained model tested on the alpha helical protein. You see it's sort of hallucinating a few beta strands, but generally speaking, this geometry more or less right. And you see the converse in the bottom case, where the middle pink structure is a beta sheet structure, but it's being predicted by the alpha helical protein, the alpha helical model, sorry. And you see that it doesn't kind of quite cover the exact hydrogen bonding networks of the strands, but it sort of knows where to place the alpha trace. Right? It knows where the atoms roughly are, even though it doesn't quite get the details. That to us was quite remarkable, sort of for it to be able to generalize this much. And now it suggests in some way, I think it does tell us something about actually the nature of protein structure space, because it suggests that at a local level, there's probably sufficient kind of generality there that even by just learning, on those local regions, is able to somehow generalize to the broader space. And that to me was pretty exciting. So let me sort of stop here with the last just this kind of a bit about this OpenFold consortium. So like I said, we sort of re-implemented the system, we've retrained it from scratch, and it seems to work exactly like AlphaFold2 did. And so now what we're interested in, so where can we go from here? What comes next, right? And so we've sort of built this kind of consortium, right? And it's kind of meant to be something that is, I think the key point here is steerable, right? So the idea is that this is something that's sort of responsive to the interests of the broader community, and particularly to industry partners in biopharma that have specific needs, right? And there's certain problems that they're really interested in going after. And I list some of these, below, things like integrating structural priors from experiments, right? Predicting, multiple conformations, or predicting complexes involving small molecules and things like that. Right? Problems that are of sort of interest to the biopharma industry. And so essentially having a kind of a scheme in place where we are doing science in the open, everything is published in the open source, but it is responsive to the needs that are kind of put out there, in exchange for supporting this sort of consortium. So we think that's sort of an interesting model. It's different than the kind of standard, certainly different than DeepMind, different than sort of standard academic groups, and it will be interesting to see how it evolves in the years to come. So with that, I'd like to particularly thank Gustav and Nazim, who sort of led most of the work on the technical side here, and some of the folks on the OpenFold organizing as well. And this is my lab. Thanks for your attention.
Thanks a lot for the great talk. It's really inspiring to see that with OpenFold, you did not just copy and paste AlphaFold and made it open, but really analyzed it in depth and built new applications, fine-tuned into new applications to really see how much it can be beneficial to the community. So thanks a lot for the great talk. And regarding the questions, I forgot to mention before that questions will be taken at the end of the presentation. And there is a microphone there where you can go so that the audience online will be able to hear what you say. So the conference is now live streamed, and I heard that there's more than 100 people attending the talk online. So if you have questions, please go in line and ask them at the microphone. We have a few minutes left.
Sorry for the long walk. So great, really exciting talk. And I think you mentioned it at the end. AlphaFold really depends on updating the sequence embedding, right? And having MSAs at the beginning of the pipeline allows it to have a good initialization of that embedding. For the single sequence problem, has there been work in AlphaFold or in OpenFold to integrate the language model embeddings and the Facebook Meta AI kind of ESM fold approach to get better representations and potentially learn structures of more disordered complexes that wouldn't be good with the current AlphaFold model?
Yeah, thanks for the question. So I should say that the Meta's ESM fold is actually built on OpenFold. So that was actually the kind of first big application of OpenFold in a way was Meta's use of it. So we're certainly interested in this problem, and it's something we're actively working on. So initially, we were, I would say, very excited about the language models for this problem. I'm a little bit less excited now, and part of the reason why this is because what we've seen, particularly with CAS 15, which is the last CAS that just happened, was that these language models seem to be, essentially learning what an MSA would learn or what an MSA would represent, but they seem to actually do so a little bit more poorly, right? So in particular, what happened is that sequences that were sort of in sparse regions of sequence space ended up doing worse with language model-based approaches than with the MSA-based approaches. So even if you're able to like retrieve 2 or 3 related sequences, that really gave an edge to the MSA-based systems, while the LM-based systems, they presumably didn't sort of learn as much because they were so sparse, those regions, that they weren't able to generalize very well. So that is maybe, so it's 2 possibilities here, and we're exploring both. One is to think differently a bit about how language models should be built in the protein context, because we do know a lot about proteins. They're all evolutionarily related, for example. That's not necessarily sort of true of natural language. And so that's sort of one direction, sort of better language models. The other is to try to do prediction without language models, guys. So just going from sequences directly and try to incentivize the model to essentially not rely on co-evolutionary information whatsoever. And that's the other direction, I would say. So yeah, we're pushing on both fronts. We'll see.
For a nice talk. It was really interesting to learn about the successes in prediction of complexes, protein complexes. So my question is actually related to this part. So I guess I have 2 mini questions. So first question, when you said the training set, you just concatenate 2 proteins, right? This would, I guess, will be applicable to stable complexes, which are not transient, which those proteins which do not exist as monomeric, right? They only would be stable in complex. And another question, and you know, PDB is actually doesn't have so many signaling protein transient complexes. It is very enriched towards very stable permanent complexes, yeah, obligatory complexes. And a related question, actually, I always was wondering, I don't know how AlphaFold solves this problem of homooligomers when protein can interact with itself. And say one protein from one organism can, with the same fold, can function as a monomer. So you would use, there is sort of one set of, would say, features, yeah? But another organism with the same fold, it will be dimer or tetramer and so on. So how also AlphaFold will solve this?
Yeah, let me start with the second question. So generally speaking, I would suspect we would have a hard time, to be honest, distinguishing between those 2 possibilities. And generally speaking, the stoichiometric state has to be given, essentially, right? So you're telling it whether this is a monomer or a trimer or a dimer or what have you. It doesn't have the capability to figure that out on its own. But you could look, for example, at the PLDT, this predicted confidence, and then maybe use that as a judge. But my suspicion would be if you have sort of 2 highly homologous proteins where small changes made one a dimer and the other a monomer, I don't think it'll pick up on that. That would be my expectation. As to your first question, there too, I mean, you're absolutely right. I mean, most of what's trained on are, you know, obligate stable complexes. It's not going to pick up on transient interactions. And what you typically see, which is sort of funny in a way, is that it's always trying to pretend like it's working with stable complexes. So for example, if you give it a peptide, right, that's sort of a low affinity peptide, it will still stick it in there as if it were a high affinity peptide. So it's always trying to kind of jam proteins into another. So in that case, I would say it's sort of non-discriminative. If you have 2 related protein peptide sequences, one is high affinity, one is low affinity, it can't really tell them apart for the most part.
Thanks again for the great presentation and the work that's been done. Maybe you said it and I missed it. Have you compared OpenFold with AlphaFold on you know, out of sample benchmarks in terms of statistical differences and things like that?
So the validation set is sort of held out, you know, out of so in that case, I mean, yes, but I mean the main stuff is the stratification of the structure space, right? If your question is, do the AlphaFold weights do better than the OpenFold weights? Yes. That's actually a very good question. It's a very obvious thing, and we should do it. Yes. Now that I realize it. I mean, I suspect they'll behave differently, but it's a good point. We should assess that. Yes, just to kind of have peace of mind. Yeah.
But what about on the CASP?
Yeah, in the CASP, it's you know, like I said, we've done so when we participated in CASP 15, but at the time we had a partially trained model. But now, you know, with a fully trained model, we've assessed it, and it's the same. Statistically speaking, they're not really distinguishable. But in that case, I wouldn't call it a distributional shift. Yeah, there it's more about like something that's sort of, you know, quite different from what it's seen, but it's still, you know, within kind of fold space. The ablation studies with the data, I think those are much more of like really a distributional shift, something very different than what it's seen.
Thanks.